Welcome to another deep dive. Today, we're diving into quantum computing and a fascinating new development from Google. So imagine a computer so powerful it could design life-saving drugs or unlock the secrets of the universe. That's the potential of quantum computing. But there's this major roadblock holding it back. Errors.
Yeah, these quantum computers, they're incredibly sensitive to any kind of disturbance. Even the slightest vibration or temperature change can throw off their calculation.
Oh, so it's like trying to build a house of cards in a hurricane.
That's a pretty good analogy. And that's where Google's new AI system, AlphaQubit, comes in. It's designed to tackle this error problem, and it's showing some remarkable results.
Okay, I'm intrigued. We've got Google's blog post on AlphaQubit and a research article from Nature to guide us. So before we get into AlphaQubit, can you remind me what makes these quantum computers so different from the ones we use every day?
It comes down to how they process information. Regular computers use bits, which are like tiny switches that can be either on or off, representing a 1 or a 0. But quantum computers use qubits, which are much weirder.
Weirder how?
Well, a qubit can be in a superposition, meaning it can be both a 0 and a 1 at the same time. It's like a coin spinning in the air before it lands. It's not heads or tails until you stop it and look.
So it's like having a computer that can explore multiple possibilities simultaneously.
Exactly, and that's just the beginning. Qubits can also be entangled, meaning they're linked together in a way that even if you separate them by a huge distance, what you do to one instantly affects the other.
Okay, my head is starting to spin a little. But I get the basic idea. Qubits are powerful, but also super delicate. So how does this AlphaQubit help protect them from errors?
It all comes down to quantum error correction. Think of it like a safety net. Instead of relying on a single qubit, you use a bunch of them together to represent one logical qubit.
Okay, so it's like having a backup system in case one qubit goes haywire.
Exactly. And these physical qubits are constantly being checked for inconsistencies. If an error is detected, AlphaQubit steps in as the decoder.
Decoder, what does that mean?
The decoder analyzes the information from these checks and figures out where the errors are and how to correct them. It's like having a detective at the scene of a crime, piecing together clues to solve the case.
Got it. So AlphaQubit is like a superpowered detective for quantum computers. Tell me, what makes AlphaQubit such a standout? What sets it apart from other decoders?
Well, AlphaQubit is actually an AI decoder built on a neural network architecture, similar to the ones that power large language models, like the ones behind chatbots like ChatGPT.
Wait, so the same tech that's helping chatbots have conversations is also helping quantum computers run smoothly. That's wild.
It is, and what's even more impressive is how well it works. In tests on Google's Sycamore quantum processor, AlphaQubit was able to reduce errors by a significant margin compared to previous methods.
So we're talking about a noticeable improvement. Can you give me a sense of how much better AlphaQubit is compared to what came before?
For sure. In one of the larger experiments on Sycamore, AlphaQubit achieved an error rate that was 6% lower than the previous leading decoder, a method known as the tensor network.
6%? That might not sound like much, but I'm guessing in the quantum world, that's a huge leap forward.
It is. You see, the tensor network method, it's known for its accuracy, but it's too slow to be practical for larger quantum computers. Another method, called correlated matching, is fast enough, but it's not as accurate. AlphaQubit seems to have found the sweet spot. High accuracy at a speed that could work for larger systems.
Okay, so this accuracy thing, it's a big deal. What does this kind of improvement actually mean for the future of quantum computing?
Well, reducing errors is essential for building larger, more powerful, and ultimately, more useful quantum computers. Imagine a future where we can simulate complex molecules to design new drugs and materials. That's the kind of power we're talking about.
So AlphaQubit is bringing us closer to actually using quantum computers to solve real-world problems. That's incredible. But the Sycamore processor is relatively small, right? What happens when you scale things up? How does AlphaQubit handle larger, more complex systems?
That's a great question. To see how it would perform on larger systems, the researchers simulated quantum computers with up to 241 qubits.
Hold on. How do you test something that doesn't even exist yet?
With simulations. Essentially, they created a virtual quantum computer and ran AlphaQubit through its paces, and the results were promising. It continued to outperform the other decoders, even on those larger simulated systems.
So it's not just a one-hit wonder. It actually has the potential to scale up as quantum computers get more powerful.
Exactly. And that's crucial because as we build bigger quantum computers, the challenge of managing errors
Yeah.
becomes even more daunting.
It sounds like AlphaQubit is a huge step in the right direction, but surely there are still challenges ahead. What are the researchers working on now?
Well, one of the main challenges is speed. Right now, AlphaQubit needs to get much faster to keep up with the real-time demands of quantum computations.
So it's like having a brilliant detective who takes weeks to solve a case.
Right.
By the time they figure it out, it's too late to do anything about it.
That's a good way to put it. And as quantum computers grow larger, containing millions or even billions of qubits, we'll need even more efficient ways to train these AI decoders. We're talking about handling truly massive amounts of data.
It sounds like a daunting task, but I'm sensing there's a but coming.
You're right. The good news is that Google's teams are already tackling these challenges. They're exploring ways to make AlphaQubit faster and more efficient. And they're looking into new training methods that can handle the demands of these future quantum behemoths.
Okay, phew. That's good to hear. But before we get too carried away with the future, can we go back to something you mentioned earlier? You said AlphaQubit was different because it's built on a neural network, like the ones used in chatbots. How does that actually work? How does a system designed for language understand and correct errors in a quantum computer?
It's a fascinating process. Remember how we talked about AlphaQubit being trained on data? Well, this training process is similar to how large language models are trained. It starts with what we call pre-training.
Pre-training, what does that involve?
In pre-training, AlphaQubit is fed a massive amount of simulated data. The simulated data is like a training ground, allowing AlphaQubit to learn the basics of error correction without the risk of messing up a real quantum computer.
So it's like learning to drive in a simulator before hitting the real road.
Exactly. This simulated data is designed to mimic the types of errors that can occur in a real quantum computer. So AlphaQubit gets a chance to practice identifying and correcting these errors in a safe virtual environment.
Makes sense. So after this pre-training, it's ready for the real deal.
Almost. The next step is fine-tuning. This is where AlphaQubit graduates from the simulator and gets trained on real-world data collected from the Sycamore processor itself.
So it's like taking that driving simulator and putting it on a real road with all the unexpected obstacles and challenges that come with it.
Precisely. This real-world data is much more complex and messy than the simulated data, but it's also much more valuable. It allows AlphaQubit to adapt to the specific quirks and nuances of the Sycamore processor and learn to handle the kinds of errors that we can't perfectly simulate.
Interesting. So it's not just memorizing solutions, it's actually learning to think on its feet and solve problems it's never encountered before.
Exactly. And the results speak for themselves. After fine-tuning, AlphaQubit consistently outperforms traditional decoders, even on larger, more complex systems.
Impressive. It sounds like this two-stage training process is key to AlphaQubit's success. But what kind of information is it actually learning from? What does this real-world data from Sycamore look like?
It's all about those consistency checks we talked about earlier. Remember, we're constantly monitoring those groups of physical qubits for signs of errors. This monitoring process generates a ton of data, essentially a history, of how those qubits have been behaving over time.
Okay, so it's like security camera footage of the qubits, showing how they've been interacting.
A perfect analogy. And AlphaQubit analyzes this footage, looking for telltale signs of errors. It learns to differentiate between normal fluctuations and actual errors that need to be corrected.
Got it. So it's like a detective studying fingerprints, searching for the unique marks of the culprit.
Exactly. But what makes AlphaQubit even more powerful is that it can learn from more nuanced data, what we call soft information.
Intriguing. What's soft information in the quantum world? And how does it help AlphaQubit?
Think of it this way. Traditionally, we measure qubit in a very black and white way. It's either a 0 or a 1. But in reality, things are a bit fuzzier. There's a certain probability of a qubit being in one state or another, and that probability can be very valuable.
So it's like saying, I'm not 100% sure, but it's more likely to be a 0 than a 1.
Precisely. And this soft information can give AlphaQubit extra clues for error correction. It's like having a witness who says, I'm not sure if the getaway car was red or maroon, but it was definitely a dark shade of red.
That extra bit of detail could be the key to cracking the case. So AlphaQubit is like a super sleuth, gathering all the evidence it can, even the subtle hints, to solve the quantum mystery.
That's a great way to put it, and this is one of the things that sets it apart from traditional decoders. They often struggle with soft information, treating everything as black and white. But AlphaQubit embraces this ambiguity, using it to its advantage.
Amazing. So AlphaQubit is playing 4D chess, while others are stuck with checkers. And this ability to handle soft information is especially important for certain types of quantum errors, right? Like those leakage errors you mentioned before.
You're exactly right. Leakage is a tricky problem because it involves qubits transitioning to states outside their intended computational space. It's like a chess piece suddenly jumping off the board and landing on a nearby table. The traditional rules no longer apply.
Sounds chaotic. But AlphaQubit seems to have found a way to wrangle these rogue chess pieces.
It has. By incorporating soft information about these leakage probabilities, AlphaQubit can accurately detect and correct these errors, preventing them from causing a computational meltdown.
Fantastic. It sounds like AlphaQubit is a major leap forward for quantum error correction. But I'm curious, what about those challenges we talked about earlier, speed and scalability? How are researchers planning to address those?
Well, when it comes to speed, it's all about optimizing the neural network and streamlining the training process. Google's teams are exploring ways to make the computations more efficient. And they're even looking into specialized hardware designed for AI tasks.
So it's like giving our super sleuth a faster car, a better lab, and maybe even a supercomputer sidekick.
Exactly. And for scalability, the key is finding more data-efficient ways to train these massive neural networks. As quantum computers grow to millions, even billions of qubits, the amount of data needed for training will explode.
Right. We can't exactly build a quantum computer the size of a planet just to train AlphaQubit.
Exactly. So researchers are looking into strategies like transfer learning, where AlphaQubit can leverage knowledge gained from training on smaller systems to more quickly adapt to larger ones. They're also exploring active learning, where AlphaQubit can intelligently choose which data points are most valuable for training.
Smart. It's like giving AlphaQubit a speed reading course and a knack for picking out the most important clues.
Precisely. And these are just a few of the approaches being explored. The field of AI is evolving rapidly, so there's no doubt that even more innovative solutions will emerge.
This is exciting stuff. It sounds like AlphaQubit is more than just a solution to a problem. It's a glimpse into the future of how AI and quantum computing will work together to achieve some truly remarkable things. But let's not get ahead of ourselves. What does AlphaQubit mean for us right now? Are there any practical applications that we can benefit from today?
That's a great question. While large scale, fully fault-tolerant quantum computers are still a ways off. AlphaQubit's success has immediate implications. For research and development, it can be used to improve the performance of existing quantum computers, even those with relatively few qubits.
So it's like giving a performance boost to our current quantum machines.
Exactly. By reducing errors, AlphaQubit can help researchers conduct more accurate experiments and make faster progress towards those long-term goals. It can also be used to test and validate new quantum algorithms and error correction strategies, giving them a more realistic testing ground.
Uh-huh. So it's like a testing ground for the next generation of quantum technologies. And speaking of next generation tech, you mentioned something about using AlphaQubit's confidence score to improve a technique called magic state distillation. Can you tell me more about that?
Absolutely. Magic state distillation is a crucial process for building fault-tolerant quantum computers. It's a way of creating high-fidelity qubits that are less susceptible to errors. The problem is, it's incredibly resource-intensive.
Like a major bottleneck for quantum progress.
It can be, but this is where AlphaQubit's confidence score comes in.
Yeah.
Remember how we talked about AlphaQubit being able to tell us how confident it is in its error correction predictions?
Right. It's not just saying error.
Mhm.
It's saying, I'm 80% sure this is an error.
Exactly. Well, we can use that confidence score to filter out low-confidence results during magic state distillation, making the whole process more efficient.
Clever. It's like a quality control system, ensuring that we're only using the most reliable qubits.
Precisely. And this could significantly speed up the development of those powerful, fault-tolerant quantum computers we're all hoping for.
Incredible. It seems like AlphaQubit has implications for both the near and long term. So let's zoom out a bit and talk about the bigger picture. What does AlphaQubit tell us about the future of quantum computing and AI's role in it?
Well, what's truly exciting is that AlphaQubit is a prime example of how machine learning can revolutionize quantum computing.
So you're saying AI isn't just a helper, but a driver of progress.
Exactly. Traditional error correction methods often rely on simplified models of how errors behave. But the real world of quantum computers is messy. Noise isn't always predictable or well-behaved.
So it's like trying to predict the weather. With a simple barometer, you might get a general idea, but it's not going to be super accurate.
A perfect analogy. AlphaQubit, on the other hand, learns directly from experimental data. It adapts to the complexities of real-world quantum systems and can handle things like leakage and crosstalk, which are issues that traditional algorithms often struggle with.
Hold on, can we take a step back for a second? What are leakage and crosstalk? I'm not sure I fully understand those terms.
Of course, leakage is a problem. That occurs when qubits leak out of their intended states. Imagine you have a container of water, and it starts leaking out the sides. That's kind of what happens with leakage. In a quantum computer, the information stored in a qubit starts to leak out, causing errors.
Okay, that makes sense. And what about crosstalk?
Crosstalk is when qubits unintentionally influence each other. Think of it like two people trying to have a conversation in a noisy room. They might accidentally start talking over each other or misinterpret what the other is saying. Similar things can happen in a quantum computer, where the qubits can interfere with each other and cause errors.
Ah, so it's like having noisy neighbors in a quantum computer. But AlphaQubit is able to filter out this noise and figure out what's really going on.
Exactly. AlphaQubit learns to recognize the patterns of leakage and crosstalk, and it can correct for these errors even when they occur in unexpected ways.
So it's like AlphaQubit has learned to speak the quantum language, understanding its quirks and nuances.
Precisely. And this adaptability is a huge advantage. As quantum computers continue to evolve and become more complex, it suggests a future where AI isn't just fixing errors, but actively shaping the design and operation of quantum computers.
Wow, that's a pretty mind-blowing thought. It sounds like AlphaQubit is more than just a fix. It's a fundamental shift in how we approach quantum computing. But hold on, before we get too carried away with the future, let's bring it back to the present. What are the most important things for our listeners to remember about AlphaQubit?
I think the key takeaway is that AlphaQubit represents a major breakthrough in quantum error correction. It's significantly more accurate than previous methods, and it has the potential to scale up as quantum computers become more powerful.
And it's not just about fixing errors, right? It's about opening up new possibilities for what we can do with quantum computers.
Exactly. By reducing errors, AlphaQubit is paving the way for us to tackle some truly groundbreaking challenges. Imagine being able to simulate the behavior of complex molecules, leading to the development of new drugs and materials, or using quantum computers to break encryption codes that are currently considered unbreakable. These are the kinds of advancements that AlphaQubit is making possible.
It's amazing to think about the potential impact this technology could have. But you mentioned something earlier that really caught my attention, the idea that AI could actually drive the future of quantum computing. Can you elaborate on that?
Of course. We're already seeing how AI can be used to design and optimize quantum algorithms. Imagine AI systems that can analyze massive data sets of quantum experimental results, identifying hidden patterns and correlations that would take human scientists years to uncover.
It's like having an AI research assistant working alongside quantum scientists.
Exactly. And AI could also play a crucial role in making quantum computers more accessible and user-friendly. Imagine AI-powered interfaces that could translate complex quantum algorithms into simple, intuitive commands.
That would be incredible. It would open up the world of quantum computing to people who don't have a deep understanding of the underlying physics.
Exactly. And that could lead to a whole new wave of innovation, with people from all sorts of backgrounds experimenting with quantum algorithms and exploring new applications.
It's exciting to think about what the future holds. AlphaQubit is just the beginning. Who knows what amazing breakthroughs await us as AI and quantum computing continue to evolve together.
I couldn't agree more. This is truly a frontier of science and technology, and it's an incredible time to be involved in this field.
Well, I have to say, this deep dive has been an eye-opener. I feel like I've gained a whole new appreciation for the power and potential of quantum computing and the incredible role that AI is playing in shaping its future.
I'm glad to hear it. It's a fascinating field, and I hope this deep dive has inspired you to learn more.
It definitely has. And to our listeners, if you're as intrigued by this as I am, I encourage you to dig deeper. There's a whole universe of information out there waiting to be explored.
And remember, the future of quantum computing is still being written. Who knows? Maybe one of you listening will be the one to make the next breakthrough.
And that's a wrap on today's deep dive. Thanks for joining us on this incredible journey into the world of AlphaQubit and the future of quantum computing. Until next time.